In Sacramento, for example, a major provider there is building up a 5G network. They have chosen to use a high-frequency 5G network. Due to this decision, they have to have a lot more radios installed and activated to get a solid 5G coverage. In comparison, another company is using its existing 4G network as a gateway to connect its 5G network. Using this method allows for the 5G radios to be accessed through the existing 4G network that has a longer range. Both of these methods tie back to the original technology and science that Maxwell helped to quantify and research within the electromagnetic spectrum. Next, we'll highlight physics in modern technology. Once again, we'll use our example from our module to talk about Einstein and relativity. Mandy took a trip to Rome, Italy. She gazed out over the open ocean 20,000 feet below as her airplane began its descent to her final destination of Rome. It had been a long flight from New York to Rome, but as she stretched, and her bones creaked as though she was old, she knew that in fact she was a tiny bit younger than her counterparts back home, thanks to traveling at hundreds of miles per hour. In fact, time for her was running slowly compared to her friends in New York for two reasons: the speed at which she had traveled and the height of the airplane above the Earth. Neither, though, were noticeable. Einstein's theory of relativity is typically broken down into two parts. The first is the special theory of relativity, which essentially deals with the question of whether rest and motion are relative or absolute, and whether the consequences of Einstein's conjecture that they are relative. The second is the general theory of relativity, which primarily applies to particles as they accelerate, particularly due to gravitation. It acts as a radical revision of Newton's theory, predicting the important results for fast-moving and/or very massive bodies. In our example, we highlight the variance in time that is experienced between Mandy while she was flying and her friends back at home. The primary theory that is present in this variance is time dilation. Time dilation predicts that a fast-moving clock will tick at a slower rate than a stationary one. Time dilation also says that velocity isn't the only thing that affects the rate at which clocks tick or people age. Gravity does too. A clock in a stronger gravitational field, the Earth's surface, let's say, will have a slower tick rate than a clock subject to weaker gravity, such as a few miles up into the atmosphere. For Mandy, she was moving at a faster speed than her friend back home in New York. Due to this action and the theory of time dilation, time is moving slower for Mandy. Additionally, since Mandy is miles above the Earth during her flight, the effect of gravity on her is also decreased. This decrease in gravity also contributes to the slower time she experiences while she flies compared to her friends back home. It is, however, important to point out that this change in time is relative, meaning all of the other passengers on Mandy's flight are experiencing a variance in time just like Mandy, because they are all moving at the same speed and gravitational pull. Similarly, the variance in time the passengers and their friends and family back home is relative to the speed and distance between the airplane and back home. In the end, the variance in time is incredibly small, however it still occurs. GPS is another example of physics in modern technology. Unfortunately, I have not experienced space travel to validate some more examples of Einstein's theory of relativity. However, I have experienced the result of this theory when I use my GPS to obtain driving directions when I travel to a new location. Global Positioning System is a network of about 30 satellites orbiting the Earth at an altitude of 20,000 kilometers. Wherever you are on the planet, at least 4 GPS satellites are visible at any time. Each one transmits information about its position and the current time at regular intervals. These signals, traveling at the speed of light, are intercepted by your GPS receiver, which calculates how far each satellite is based on how long it took for messages to arrive. In order for the atomic clocks aboard the satellites to keep accurate time, Einstein's general and special relativity concepts are applied to these clocks. General relativity predicts that since the satellites are traveling in an area of less gravitational pull relative to the clocks on Earth, the clocks on the satellites will run faster than the clocks on Earth. Special relativity predicts that because the clocks on satellites are moving relative to the clock on Earth, they will appear to run slower. Due to both of these effects, the whole GPS network has to make allowance for relativity. Last, we're going to discover quantum mechanics and some examples of quantum mechanics in current day. Today, the most precise clocks in the world are atomic clocks. They're able to use principles of quantum theory to measure time. They monitor the specific radiation frequency needed to make electrons jump between energy levels. The quantum logic clock at the U.S. National Institute of Standards and Technology in Colorado only loses or gains a second every 3.7 billion years. The efficiency and accuracy of atomic clocks helps with GPS navigation, telecommunications, and surveying. In regards to GPS navigation, there are at least 4 satellites visible to a GPS-capable device at once, as mentioned earlier. Each one transmits information about its position and the current time at regular intervals. These signals, traveling at the speed of light, are intercepted by your GPS receiver, which calculates how far away each satellite is based on how long it took for the messages to arrive. The atomic clocks within the GPS units and satellites are responsible for making the overall technology work. Basically, the entire computer industry is standing on the principles of quantum physics. All the semiconductor electronics based on the band structures of solid objects rely on quantum physics. This is because of the wave nature of electrons, as we can manipulate the electrical properties of silicon. Piling up the layers of silicon doped with different elements help us to make transistors on the nanometer scale. However, hundreds and hundreds of these packed together in a single block to make computer chips, which power the technological gadgets that are very important in our modern day. One of the most common computers we carry in our pockets every day is a smartphone. Quantum mechanics has allowed us to create devices capable of taking pictures, browsing online, sending messages, and many more functions in the palm of our hand. Additionally, as the production of the components required in building a smartphone become more and more efficient to produce, the continued growth in the capabilities of our smartphones will continue to grow. Quantum mechanics is also present in the invention and use of magnetic resonance imaging. According to our module information, during an MRI, the strong magnetic field passes through the body during an MRI, causes the protons and water molecules to align with the field. A radio frequency wave is then turned on, causing some of the protons to align differently. When the radio wave is turned off, the protons return to their preferred state and give off energy. This energy is used to create images of different structures in the body. One important feature of an MRI is the fact that there is no radiation used during this process. This will make the use of an MRI a safe and accurate method to leverage during neural imaging. The use of MRI scans has provided researchers with a significant amount of interesting and valuable data about the brain and how it operates. Lasers are another technology that form quantum mechanics. While there are many different applications of lasers around us, one application of lasers that helps me in my workplace is our scan guns that can scan the UPC barcodes on our products. While I do work in the smartphone industry, which in itself is a direct result of quantum mechanics, the use of lasers to scan our products makes my job much easier. Each fiscal quarter, we are required to do a physical count of all our accessories and devices in our store. The first in-service laser scanning of an item with a UPC symbol, a pack of Wrigley's chewing gum, occurred at a supermarket checkout counter in Ohio. Now used globally in dozens of industries, barcodes are scanned billions of times daily and are claimed to save billions of dollars a year for consumers, retailers, and manufacturers alike. Much like this article highlights, every item in my store's inventory has a scannable UPC. This UPC may be an accessory SKU, SIM card number, or serial number of a device. Thanks to quantum mechanics, we were able to use a scan gun with a laser to scan all of these items. Prior to the UPC automation in our retail locations, we would have to hand count every item using a pencil and clipboard. Using the scan guns and UPC barcode is much more efficient and accurate for overall operations of our business. While there is an initial investment in shipping every store in our company's scan guns for every computer in a retail location, the accuracy of scanning an item instead of manually keying or counting an item has greatly decreased our internal shrink or loss of goods, which leads to an overall positive impact on our business. That concludes our presentation today. Thank you for listening and for allowing me to share with you some examples of physics throughout history and the principles and how they impact our world today. Thank you very much. Goodbye.